a.m. to 1 p.m., so it lasts for 2 hours. You don't have to come for the entire 2 hours, but if you've got a half hour to spare, come on by. It's in Avery 348. It's our biannual student advisory panel. We hold this every semester. It's basically an opportunity for you to come and give feedback on your the courses that you've been taking, the department, the resources that you've been that are available to you, the programs that you're taking. And this is probably your first course if you're a major. That's fine. We still want your opinion. So if you want to come by and have some free pizza, it's usually Papa John's, but I'm not sure. I didn't order it. And it's going to be on this Wednesday from 11 a.m. to 1 p.m. And again, that's in Avery, third floor, 348. Okay. All right, so to get to, thanks, there we go. To get to today's topic, what is recursion? Again, we're only going to cover recursion for one day. Lots of people like to, or some instructors like to dive deep into it and get it really into recursion, give it several weeks or something. I don't, and you'll see why by the end of the day, why I don't like to get into it. But what is recursion? Well, let's just ask Google here first of all. We're going to go ahead and search for recursion. And there it gives a definition, but maybe I made a mistake here. Did I make a mistake? All right, let's go ahead and see. Okay, I made the same mistake. Just click it again, click it again, click it again. And now you get the joke. What is recursion? It's anything that refers to itself, right? I'm caught basically in an infinite loop here of recursion. What is recursion? Well, recursion is recursion. What is recursion? Recursion is recursion. That's what it's answering here. So from a more general sense, in general, recursion is something that references itself. It's self-reference. And you've probably seen several examples without really knowing it up to this point. Example would be fractals. Right? You might not have seen the word fractal, or you may have, but let's look at one of them. Sierpinski. I don't know how to spell it. I'll let Google correct it for me, and let's just look at some images here. Basically, fractals are self-similar objects. Let's go ahead and look at one in particular here. The way that the Sierpinski triangle, for example, is constructed is you start with a triangle, and then you cut it into the triforce, basically, and you take out that center triangle. Then you do it again on the triangle above, the left one and the right one, right? And then you do it again and again and again. It's a self-referencing build, right? So how do you build the next one? Well, it's exactly how you built the last one, but you recurse on a smaller triangle. Or you might have seen even prettier pictures, like, I don't know, the Mandelbrot set. There we go. So these fractal art pictures are always popular to look at and play with. They all have self-similarity. Basically, if you zoom in on a Mandelbrot set, it looks like the Mandelbrot set. Because, again, is a recursive definition. What does the smaller piece look like? It looks like the bigger piece, just smaller. Right? It's self-referential, and that's how you build fractals. Another example that you've probably seen before, other than that, is maybe the Fibonacci sequence. Right? So for that, I'm just going to cut and paste some math here. Here we go. This is the classic good-bad example. 9 times out of 10 when I see recursion introduced in a course or in a new programming language, the go-to example is going to be the Fibonacci sequence. And for our purposes, it's going to be defined like this. Sometimes they start off by 1 or something like that, or the first number is 0 and then you go to 1. But basically, you start at 1, 1. Right? So the sequence is going to be you start at 1, and then the next one in the sequence is 1. And then the next value in the sequence is, this is the third line here, is the value 1 previous to the sequence plus 1, 2 previous to the sequence. So if I start out with 1, 1, then the next one in the sequence is simply going to be 1 plus 1. Right? So it's 2. Well, now what's the next one? It's the addition of the 2 previous ones. So 1 and 2, it's going to be 3. And you see the pattern start to emerge here. What's the next one? It's going to be the 2 previous ones added together. It's 5, 8. What's next? 13, 21, 34, 55, 89, and it's a sequence, so it goes on forever and ever. There we go, L dots, there we go. It goes on forever and ever. How do you think this sequence is growing, by the way? Exponentially, right? And that's going to come into play later on, right? So again, it's a good bad example because it's always first of all, there's nothing special about the Fibonacci sequence. It's nothing more than a second order linear homogeneous recurrence relation of degree 2, and when you hit 235, you're going to learn how to solve those really easy, right? It's just a plug and chug kind of formula thing. You I won't even go into it now, but it's like a 3 or 4 step process, and you get this nice closed form solution, which will also come into play later on here. Don't worry about it, right? There's nothing mystical about it. People try to make it more than it is because of the golden ratio. The Fibonacci sequence gives you the golden ratio of 1.61. And if you look at, again, you get nice, pretty pictures out of that one too, right? It's great for drawing nice, pretty pictures. Mathematically, though, big deal, right? All it is a second order linear homogeneous recurrence relation of degree 2 with constant coefficients of 1, and those are a dime a dozen. Just change your constant coefficients, change your degree, and you get different results, right? So there's nothing mysterious about it, but a lot of people like to attach a lot of meaning to it, like, ooh, it's a golden ratio, it's a bunch of other mystical stuff that comes along with it. For our purposes, however, recursion in coding refers to a function or method that makes calls to itself. Right? This is not that mysterious. We've been writing functions that call other functions the entire semester. Right? If you've got a main function, that's always your main entry point. That's a function. Guess what it does? It calls other functions. Right now you're putting together a bunch of string functions. Say concatenate. And hopefully you realize that that concatenate and append are a synonym, so they're probably the same function. You could have your main call concatenate, and then there's no implementation there at all. It simply just delegates it to append. You have concatenate, call append. So you've got main calling concatenate, calling append. Maybe append is calling strcat. So you've got function, calling function, calling function, calling function. All we're doing now with recursion is that this function, instead of calling that function, it's going to call itself, right? And that's all recursion is. So let me go ahead and start with a motivating example. I'm going to give you a challenge. All of a sudden, you now live in a world where you don't have loops, all right? Print a countdown from 10 to 1, then blast off, right? So it's a countdown to a blast off, right? Without using a loop. You now live in a world without loops. Not that far-fetched. This is not an artificial problem, by the way. You have many programming languages out there, functional programming languages. Their paradigms called functional programming languages do not have loops, that do not have variables. Instead, it's just function after function after function. So you simulate loops by making recursive calls instead. Pascal, Lisp, these are functional programming languages that are popular, not that hugely popular when it comes down to it, at least in the real world, but people, they're advocates for it, and they love functional programming languages. Let's see what that looks like. So I'm going to go ahead and go over here to REPL and maybe resize this here so we can see it. There we go. All right. So I'm going to start by writing a function called countdown. Right? That'll take an integer. Now the idea of this function is that you're given a number n. And if n is, say, 10 or 9 or 8 or 7 or 6 or down to 1, if it's one of those numbers, you're going to print that number. All right? So let's go ahead and write a conditional. If n is, let's say, greater than or equal to 10, then we'll go ahead and print that number. Printf, we know how to do that. That's pretty simple. Just go ahead and print it. All right? And it's a void function. It's not going to return anything whatsoever. So if we're given 10, it'll print 10. And then, as it is right now, it'll be done. If we're given 5, it'll print 5 and be done. If we're given 1, it'll print 1 and be done. Right? The case that we want it to print blast off is when? If we count down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, When we get to 0, that's when we want it to print blast off instead. Right? So let's go ahead and put that as a condition. If n is 0, then we'll go ahead, instead of printing the number, we'll go ahead and print blast off. Right? And then end the line. Okay? And then I'll go ahead and combine these two. They are mutually exclusive, so we've got an if and an else if. Otherwise, if it's greater than or equal, not greater than or equal to 10, greater than or equal to 0, or not equal to, greater than 0, there we go, then it'll print that number. But still, this is only one call. This is not a recursive function yet. This function is not calling itself. We need to set ourselves up for the next countdown. If I were to call this, say, from the main, count down from 10, right? Then all it's going to do is print 10 and return and be done with it. We want it to do something else. We want it to then go on and print 9, and then we want it to go on and print 8, 7, 6, 5, 4, 3, 2, 1 until it gets down to 0, in which case it prints blast off. How do I do that without a loop? After it's printed the number, say 10, we want it to print 9. Well, I could, printf 9, right? I could do something like that, but that's not that's going to hard code those values. I have a function that counts down though, don't I? Countdown. It'll print whatever number that you've given it, and if it's 0, it'll print blast off, otherwise it'll print that number, right? Let's call that function instead. Countdown. What do I pass to the function now though? I could pass n. What's that going to do? Let's find out. Crossing my fingers here. Let's hope that it doesn't crash or anything. All right. It is still running because there's a stop sign there. Even though, okay, finally it died. Why? Well, first of all, what happened here? Let's walk through this function. 10 came into this function. It's not equal to 0, so it doesn't print blast off. It is greater than 0, so it prints 10 and then calls countdown on 10. Then it calls, then that gets printed. Then it calls countdown on 10, countdown on 10, countdown on 10. What kind of a trap are we in here? An infinite loop, right? This is an infinite loop here, but it didn't go on forever, right? It eventually died. Why? So think about function calling function calling function. When you call a function, remember this pile of dishes that you have? This, what did we call it? Stack. We've got this stack of dishes. Every time a function calls another function, we put another dish on the top. Remember, that is called a stack frame. So we've got this stack frame here with 10, another stack frame with 10, 10, 10, 10, 10, 10. What eventually happens? When your stack gets too tall, it's going to be fall over. That's called a overflow, stack overflow. And that's what happened here. Right? We eventually got down to the point where we had so many stack frames that we overflowed the stack because we got stuck in an infinite loop. So I don't want to pass in n. I want to make progress towards that blast off condition. If I start at 10, what's the next one I want to print? 9. If I start at 5, or if now I'm in the middle of the countdown, I'm at 5, I want to print what next? 4, right? So I need to make progress by simply subtracting 1. Now, when I do this, there, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. And I don't see a for loop. I don't see a while loop. I don't see a do while loop. And this is not in C, but I don't see a for each loop, right? That's how you do recursion. The recursion is basically a tool to simulate a lot of things that you don't have, say, in functional programming languages. Okay. Using this as an example, let's go ahead and define. In fact, I'm going to go ahead and cut and paste this over here so that you can. There we go. So that it's in the notes there. So if you want it, it's in the notes when they get posted today or later tonight. Let's go ahead and define or identify several aspects that are part of this recursive function. Recursive functions have several aspects. Right? The first one is a base case. It is a condition or case in which the recursion stops, right? I.e., no more recursive calls are made. Sounds kind of like a loop. right? A loop has an initialization condition, a termination or continuation condition, and then an increment that makes progress towards that terminating condition. Our base case is that terminating condition. You've got to stop sometime, otherwise, as you saw, you have an infinite loop. And an infinite loop with stack frame on top of stack frame is eventually going to lead to a stack overflow. So you need a base case in which you stop the recursion. You no longer make any recursive calls. Moreover, each recursive call must make some progress toward the terminating condition, right? Or to the base case, I should say, the base case, since we use that terminology up there. How was I making progress towards the termination condition, or to the base case here? The base case is when n is 0. So if I start at 10, I make progress by subtracting 1 on each recursive call. I'm making progress towards that 0 by diminishing n 1 each time. Okay? You also have some, we didn't have, take care of it here, but you also have corner cases. Corner cases may need to be handled separately. For example, spell check me. There we go. All right. What's a corner case here? I could do a countdown from 100, right? Let's go ahead and go back to the code here. And instead of counting down from, well, let's do 20 instead, so it's not too long. Count down from 20, fine. Any higher number, it's going to be perfectly fine. But what about, I don't know, -10? What's going to happen here as it's written? It's also going to be a stack overflow because it's going to be an infinite loop. You start at -10, you never reach your base condition because your base condition is up here. You start down here, and then -11, -12, -13. Let's see it in action here. And again, it's getting, come on. There we go. Oops. Oh, good point. Right. So, idiot that I am, I meant to put in, I wrote the correct one the first time. I meant to put in the mistake here of what happens when it starts below. So else if, and let's see. That's all right. I won't deal with it any further. But if we could handle this corner case instead. If n is less than 0, then we could simply return. Else if we could simply return. I don't know. Print out an error message. Printf. Negative values are not supported, and then simply just return, right? And that's kind of another base case here. And so let me go ahead and, yeah, negative values are not supported, right? Because nobody ever counts down from a negative number all the way down to -infinity, right? All right, so, I screwed up on the and wrote it correctly the first time. I meant to write it incorrectly the first time. Sorry about that. All right, so and again, a recursive function is simply a function that makes one or more recursive calls to itself, right? And as we've already seen, deep or infinite recursions may result in stack overflows. If you don't make progress toward your base case, or if your base case is wrong, then you can then you'll go on an infinite recursion, right? Recursion can be a good and useful tool, right? Many divide and conquer algorithms use recursion, right? For example, what we're going to be looking at next is searching and sorting. One of the first things that we're going to look at is binary search, where you can basically cut a list in half each time by making a single comparison. You're searching for a needle in a haystack, basically. And you can divide and conquer this array. You divide it by dividing it into two sections and deciding if my element exists, is it over here or over here? That's how you conquer it. Okay, I can throw out this half. Now, I only need to search in this half of the list. You do it again. You cut it in half, and now you've got a smaller list. And a smaller list, and a smaller list, and a smaller list until you find what you're looking for, or you no longer have a list. You divide and conquer. Usually those things are presented as recursive algorithms. In practice, though, I've never seen a real implementation that uses recursion. It either simulates recursion or it uses a recursive hybrid like Tim sort or something like that. Yeah. It divides it in half. Yep, on consideration. Yep, you're assuming that it's sorted, right? We'll get to that when we look at the next module, searching and sorting. All right, it can be a good and useful thing. Lots of people really like it. Many programming languages use recursion as a fundamental control flow mechanism. Again, those recursion. There we go. Those functional programming languages, Haskell, Lisp, OCaml, or a bunch of others, they either don't have loops, or they really try to get you to not use loops and instead prefer recursion. Right? So there are lots of proponents of it. There are lots of people that say, yeah, you should think recursively. You should write everything recursively. In fact, I think something like 20% of the nation's CS1 courses start out with a functional first approach, where they cover, say, a functional programming language like Lisp or Haskell first. They are a minority, and they're probably a diminishing minority, but they do have their proponents out there. So even though I'm going to say, well, recursion probably sucks in practice, there are probably going to be plenty of people out there that will have a difference of opinion, and then it's a healthy debate, and you can go to that side if you really want to, the dark side or whatever. Right? All right, but there are now I'm going to argue my side. There are plenty of problems. Right? Recursive functions essentially abuse the stack space by creating stack frames. That countdown, even when it worked, we made 10 function calls. Therefore, we would have 10 stack frames with 10 different parameter values. The first stack frame would have n being 10. Then the next one would have another copy of n with a value of 9 because we're passing it by value. So essentially, we have 10 variables, 10 frames. Why didn't you just write a loop to begin with? For int I starting at 10, I is greater than or equal to 1, I minus minus. Now you've got one stack frame, one variable, and you're just changing the value of that variable. The creation and the popping of stack frames, it's cheap, but it's not free. Right? And as we've already seen, deep or infinite recursions can lead to stack overflow. You abuse the stack space enough, and eventually it'll come back to bite you as a stack overflow. Right? Also, any recursive function can be rewritten as a non-recursive function. Now, there are technicalities here. There are plenty of mathematical recursions that cannot be unfolded into non-recursive values. But anything that is computable, anything that you can write a computer program to execute a recursion, you can unfold that recursion. In other words, you can get rid of the recursion. Many early programming languages didn't even allow recursion. Pascal, for example, didn't allow recursion at all. Attempting to do that would have been a compiler error or an interpreter error or something like that. They only added recursion later on. Right? So any recursive function, you can take and rewrite that. And here's the prime example. All you need is a simple for loop here. Recursion can often be simulated using an in-memory stack. In other words, don't abuse this. If you want the behavior of a stack, like a stack frame, like a program stack with stack frames, go ahead and do it. Go ahead and create your own stack that's on the heap and abuse that one all you want. Just don't abuse the call stack because it's small and defenseless. Right? So don't abuse the stack space, abuse the heap space to do that if you really wanted to. Some organizations even ban the use of recursion. Right? For example, NASA When you've got the style guide for NASA says that you cannot have unbounded recursion in any of your code because of these risks. Abusing the stack space. Embedded systems often try to get you not to use it because the stack space is even more limited in an embedded system, right? There are things that you can do to mitigate the risks of these. You can use tail recursion. You can, well, not use recursion at all, etc. But the biggest thing that I'm going to show you one way of avoiding it. And it goes into one of the bigger risks here. Recursion risks needlessly recomputing the same values over and over. Right? For example, we're going to come back to the Fibonacci sequence now. Fibonacci, okay? Let me see. I should have started this. I don't even know if this will work. Come on. That's all right. I'm not going to wait for it. Let me go ahead and left projector, my left or their left? Let's see, image blank. Okay, screen up. There we go. Let me draw you a picture. Chalk seems to be dwindling. All right. Let's call Fibonacci of 10. And if you look back on your notes, you'll see that 10, I believe, had a value of 89. What I'm going to draw is a recursion tree. So here, Fibonacci of 10 is going to make two recursive calls to Fibonacci of n-1 and Fibonacci of n-2, right? So if n is 10, then it's going to make one recursive call to 9 and another to 8. Right? And we'll actually write this function here to illustrate what I'm illustrating up here right now. 9 makes another call to -1 and -2, so 8 and 7. 8 makes two calls. It makes it to 7 and 6. Okay? 8 makes two recursive calls of 7 and 6. 7 makes two recursive calls of 6 and 5. And you start to see the pattern emerge here, right? And this is 5 and 4. Let me go one more level here. 6 and 5. This is 5 and 4. This is 5 and 4. This is 4 and 3. 5 and 4. 4 and 3. 4 and 3. And this is 3 and 2. Right? And so you've got several more levels here until you get down to ones and zeros. What I want to focus on here is how many times did I call each one of these values? Right? So here's the value. And here's the number of calls. Right? Value n. So on 10, I only made one call, right? Because that's at the top. But what about 9? How many 9s do you see here? And again, we're not going to go all the way down here. You see 1 9, right? Okay. How many 8s do you see? I made 1 2, right? Why did I make the same function call twice to recompute the same value twice? Right? It doesn't make a lot of sense. But that mistake is going to compound. How many times did I call 7 here? 1, 2, 3. Right? How many times did I call 6? 1, 2, 3, 4, 5. Right? What about 5? Not all of them are going to be here. Here's another one. Here's 5 and 4. 1, 2, 3, 4, 5, 6, 7, 8. And I know I didn't miss any. Why? What do you see on the right-hand side there? 1, 1, 2, 3, 5, 8. What's the next number going to be? 13. What's the next number going to be? 21, right? So, what does it look familiar? What is it? It's the Fibonacci sequence. And as somebody already noted, they had a good intuition. It's going to grow exponentially. Right? Let me go ahead and put the screen back up here. And screen down. There we go. Let's go ahead and implement this. And poor old REPL here. I don't know if it's going to handle it. I'm going to switch over to a long here. Fibonacci int n. Right? So this is going to be our implementation of the Fibonacci sequence. And just so that you remember, here it is again. Right? What are my base cases? Let's write yet another example of a recursive function. I need to handle the base cases. I need to handle the progress towards those base cases. So the base cases are going to be n is 0 and n is 1. In both of those cases, what value should I return here? 1. So let's just make a check. If n is 0 or if n is 1, then I will simply return 1. Now note here, my return type is going to be a long. That's so that I can represent larger numbers, slightly larger numbers. All right? We haven't really covered long, but that's going to be an integer. It's a 64-bit integer, so you can represent up to 2 to the 63 minus 1. Else. Okay? What else do I do now? I make one recursive call to Fibonacci of n minus 1, and another recursive call of Fibonacci of n minus 2, and I add them together. Let me do that. Else return, well, what's my function called? Fibonacci of n minus 1 plus Fibonacci of n minus 2. And it's as simple as that. Let's go ahead and test this. I don't care about countdown anymore. So int x is equal, or let's go with n is equal to 10. Let's compute the 10th Fibonacci number. Print, or int, or long, sorry. F is equal to Fibonacci of n. Right? And printf Fibonacci of %d equals %. To print a long, you need to use LD, long digit, and then n and f. There we go. Let's run this and see if it actually works. 89. Sound familiar? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We were right. So what's the next one? 55 plus 89 is going to be? What is it? Okay, you're going to force me to do it in my head. 130, 142, 144? Is that right? Doesn't sound right. Okay, it is. All right, 144. What about 12? Or you know what? What about 20? What's the 20th Fibonacci number? Let's go ahead and run this first of all. 1,000 or 10,946. Let's get a second opinion. What's the Fibonacci of what was it? What did I do? 20. Right. Now they're going to be starting from 1 instead. Or they're going to go 0, 1, 1, 2, dot, dot, dot. So we're off by 1 here. I would need to correct for that by going to Fibonacci of 21. That's just because they have a slightly different definition of it. Looks right to me. All right. Well, what about the 100th Fibonacci number? Understanding again that I'm going up by 1. That's big. That's millions, billions, trillions, quadrillions, quintillions. So 537 quintillion. Okay. Let me go ahead and run that for 100. We'll just sit here and wait. Okay. Now, do you think it's a good idea for me to sit here and wait? Give me an estimate. How long do you think this will take to run? 5 minutes? Okay. I'll let it run in the background. And I'm going to go ahead and show you another demonstration here. All right. Instead of relying on REPL here, let me go ahead and open up the demo here. So I've got the exact same thing here, and I've got the countdown still, and then I've got the exact same thing basically here, but I'm taking it as a command line argument instead. Okay. So gcc demo.c. Let's run it for, again, 10 should be 89. Great, that still works. 20 was, that sounds right. All right, well, let's go 40. 1, 2, 3. Oh, okay, that was pretty quick. I want to get an exact time, though. So what I'm going to do is I'm going to run this through a Unix utility called time. That's going to time it and give me an exact amount of time, 2.6 seconds. Right? The U here is for user time. All right, that's 40. Let's make sure that it's right, first of all. 41, again, correcting for their different definition. That was 165 million. Did we get 165 million? Yep, that looks right to me. Let's go with 41. How many? So it took 2.6 seconds before. What do you think it's going to take now? 3 seconds? Okay. About 3.6 seconds. Okay. Let's go up to 42. What do you think now? 5? Okay. 6.6. All right. Let's go more. All right, you're seeing a pattern here. What's the pattern that you're thinking it is? It's exponential, so you're about doubling it each time. Let me go ahead and go to 44 here. So that does 10 seconds. Let me make my prediction here. 10.28 seconds. In fact, I'm going to use Wolfram Alpha here. What was it? 10.28. 28 seconds times 1.6. I'm going to say, oh, wow, it's taking forever. I don't know why Wolfram, come on. There we go. I think it's going to take 16.48 seconds. And that was close. Closer than you are? Okay. Let's go ahead and go one more. It's not. It's also not Price is Right, so it doesn't matter if you go over or not. I think it's going to take 26 seconds on this next one, or thereabouts. Now, why was my estimate times 1.6? That's the golden ratio. If you solve for the Fibonacci sequence, you get this exponentially growing function, and the base for that is about 1.6 whatever. 27 seconds? Pretty close, right? Okay. I guess. All right. If we started, let's go back to 40 here, because again, we wanted. Let's see if the other one's done yet. Is it done? Nope. It's still a stop sign there. So let's go back to 40 here, and that was 2.6 seconds. So let's go to Wolfram Alpha here. 2.6 seconds. Now I'm going to have, if I keep going up by 1, then it's going to be then the time that it takes to do it is going to go up by a factor of 1.6. So if I go up from 40 to 100, I'm going up 1.6 times 1.6 times 1.6 60 times. Right? That's how many seconds it's going to take. Now that's seconds. Seconds aren't that much. So let's go ahead and get a feel for that. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365.25 days in a year because of leap years. It'll take us 145,000 years to see this execute. So, is it a good idea for me to sit here and wait for this? We can do it. All right, I'm going to stop it because I don't have 145,000 years to sit here and wait. Well, okay, get a REPL sucks, right? Let's go ahead and get a 1080 Ti GPU card and make it 10 times faster. Well, if it's 10 times faster, how many years are you going to wait? 14,000 years. Great. All right, make it 10 times faster again. Now it's only 1,400 years. Right? You will never catch up by playing that game. You will never catch up by simply saying we can go ahead and build twice as fast of hardware. Because there's no way, all I have to do is go from the 100th Fibonacci number to the 101st Fibonacci number, and I just erased all of your gains by going up, by improving your hardware. Right? This does not scale. It is exponential. That is a terrible way of computing this stuff. Recursion is clearly not the way to go for this. Okay? So let me go ahead and go back to the notes here. All right. And, all right, well, how do we eliminate recursion? Right? Again, we've already seen that you can always rewrite a recursive function to using non-recursive code. Right? You can use an in-memory stack to simulate recursion. Right? Those are two solutions. Another solution that I'm not going to go over in detail, but you can take a look at the book, is that you can use tail recursion and rely on the compiler to optimize your recursion away. Right? And GCC will do that if you know how to write tail recursive functions. GCC will. You don't have to have stack frame after stack frame after stack frame. All you need is GCC will realize, wait a second, you only need one stack frame, and then I'm going to rewrite this variable for you over and over and over again. In other words, if you had written a for loop to begin with. That doesn't exactly turn it into a for loop, but it basically has the same impact. So you're not abusing the stack space, and you only have one copy of your variable instead. But what I'm going to show you is instead, you can use what's called memoization. That is not a mispronunciation. That is not a misspelling. It is called memoization. Right? It's not memorization. It's memoization. Here's the basic idea. Right? You want to avoid repeated computations of the same value. Right? In other words, now this is covering it up a little bit, but I don't want all these 5s here. I don't want to make however many recursive calls, 8 recursive calls. I'll resign myself to the fact that we're going to have to make one recursive call to at least compute it the first time. But once I've computed it over here, I don't make this recursive call, this recursive call. I don't make all those other recursive calls. Instead, what I do is I save that result. I save that result into a table, or in this case, an array. That's what memoization is. So again, the idea is that you pay for the recursion if you have not already computed the value. Right? Once you've paid for the recursion, you store, that is, you cache the result. Right? Subsequent recursive calls. Subsequently, instead of making a recursive call, you check the cache. There we go. Let me move this down. Sorry. If it has already been computed, you use it and do not make a recursive call. Right? Memoization. It's kind of like memorization in that you keep all of the values that you've stored up to this point in a table or in an array. And then you don't need to pay for all that recursion. You just make at most one recursive call. Basically, it cuts out these branches. And just to visualize that, once you've paid for the recursion for this 8 over here, you don't have to pay for the recursion for this 8 over here. So this entire tree is gone. Right? And now you're not making all of those additional recursive calls. If this is a recursion tree, what do you call it when you cut a branch off of a tree? You trim it, right? You're trimming the tree by doing this. You're trimming the recursion out by eliminating it entirely. And we do use that terminology. We trim the tree, or usually they call it pruning the tree, because trimming the tree is like Christmas stuff, and you cut the tree indiscriminately. Pruning, make sure that you're doing it correctly. You only prune what you don't want, and you keep everything else. Now, if you prune the tree down to only what you want, then it starts to look like just a stick, right? You only have this one branch of recursion where you're computing all these things. That's what I'm going to show you for the rest of the day here. Let's go ahead and do a demonstration in C. Right? We're going to go ahead and use memoization to compute the Fibonacci number, eliminating redundant recursive calls. And by the way, if you're interested, memoization is nothing more than a top-down version of something called dynamic programming. Dynamic programming, basically you're going to be doing that in Thursday's hack. You're doing dynamic programming for the binomial coefficients. Although we don't call it binomial, we don't mention any of that. You don't need that kind of level of detail. We just show you how to do it, basically. Okay? So let me go ahead and copy demo here to memoization.c instead. And let's go ahead and work on that instead. I'll go ahead and leave that for now. Let's go ahead and get rid of countdown here. And here's my first step. All right, so I've got n here. What I'm going to do is I'm going to initialize a table, a cache. And we do pronounce it cache in CS. Alternatively, you could call it a cache, but usually it's a cache of weapons or something like that. We call it a cache. A cache is nothing more than a storage area where you store results so that you can reuse them right? So what I'm going to do, step 1, initialize a cache of values to be stored, right? So that we can look these things up in the table in a table instead. And here's the idea: we're going to have, I don't know, let's call it a table, right? A fib table, right? And fib table is going to be basically 0, 1, 1, 2, 3, ... right? It's going to take on all those values. Basically, the first one at index 0, it's going to be 0. At index 1, it's going to be 1. At index 2, it's going to be 2, et cetera, et cetera. So now we're off from the original definition here, but now we agree with Wolfram Alpha instead. Okay? Or do we? No. We're on this. What was our original definition? 0 is 1. Okay, so let's go with our original definition here. All right, there we go. It's going to hold those values up to the nth value. Right? The nth value here, that's going to be the one that we're interested in. Okay? So let me go ahead and just go ahead and create this table. First of all, it's going to store longs. So long star fib table, or lone star, I guess that would be. I was thinking Texas there. Long star malloc and size of long times. How big is it going to be? N? All right. That'll work if we started at 1, but do we start at 1? We're starting at 0. So 0, 1, 2, say that n is 5. I want to go from 0, 1, 2, 3, 4, and 5. How many are there total then? N plus 1. Right? There we go. There. Now, step 2, what I'm going to do is I'm going to initialize the values in fib table to flag values that indicate the real value has not yet been computed. Okay. Well, what's a good flag value here that I could use to say that I have not computed this yet? What could I initialize it to? I'm going to be looking at this table, right? I'm going to be looking at fib table of 5. Has it been computed yet or not? If it's been computed, fib of 5 was, what was it? Now I forget. 0, 1, 2, 3, 4, 5, 8. I'll look at that. Oh, 8. Okay, I'll use that value here that's stored in this table. Right? What value says to you, oh, no, I haven't computed that one yet? It could be 0. Why 0? Is there any value of the Fibonacci sequence that's 0? No. So I like that idea. Let's go ahead and do that. For int I equals 0, I is less than or equal to, or less than n plus 1, right? Because that's the size of it. I plus plus. Fib table of 0, or I, excuse me, is going to be 0. There we go. Now, step 3. And note I'm doing all of this in the main. This is just setup. We haven't even called the recursive function yet. 3, I'm going to initialize your base cases. Right? The base cases are where recursion does not occur. Where does recursion not occur here? When n is 0 and when n is 1. So I can take care of those immediately. Fib table of 0 is equal to, what's the actual value of Fibonacci of 0? 1. Fib table of 1 is also 1. Right? I could initialize other base cases if I want. I could keep going, fib of 10, 5, 10, 15, whatever. But I'm going to leave it at the 2 base cases here. Right? We're going to pass in Fibonacci and fib table. So we are going to have to change this function here. Okay? Long star fib table. There we go. Now, I come in here, and I don't care about my base cases anymore. Right? Instead, what do I care about? You want the nth Fibonacci number. I'm going to look at that table, fib table, and I'm going to determine, is the nth value already computed? Right? So if fib table of n, how do I know that it's already been computed? If it's not equal to 0, our flag value, right? In other words, Fibonacci of n has let me go ahead and put this in Fibonacci of n has already been computed. Use it. Right? So how do I use it? Well, it's already been computed. I don't need to recompute it. I just simply, what am I going to do with that value? I'm going to return it. Return fib table of n. Otherwise, at this point, Fibonacci of n has not yet been computed. So pay for the recursion. But I'm not immediately going to return that value. Instead, I'm going to store it off. Long x is equal to, there we go. Now, I am going to return x eventually, but what do I want to do to make sure that I never have to compute the Fibonacci of n again? I'm going to put it into that table. I'm going to take that value, x, and I'm going to store it. Fib table of n is equal to x. Okay? Now let's go ahead. I think that's good, right? And then, of course, corner cases if you really want to. Let me go ahead and compile this, make sure that everything works. Oops. Okay. I used an inner for loop, so std equals gdu and u 99. There we go. All right. And what's wrong? Oh, too few arguments. Duh. All right. What did I not do with my recursive calls here? I didn't pass on the Fibonacci table here. Fib table and fib table. There we go. Let's try that again. GCC. Okay, now everything works. Let's do some regression testing. That is, we made changes to it. Let's make sure that what was passing before still passes now. Fibonacci of 10 should be, I think 89, still works. Fibonacci of 20, I forget what it was, but it was like 10,000 something. Yep, 10,946. Do you remember what 40 was? 165 million, good memory there. All right, what do you think about 45 now? I forget how long it took us, like 29 seconds or something? 28 seconds? Did it take us 28 seconds there? Time, or not Tim, time, A dot out, 45. Took us no time at all, right? What about, now this is not going to work because of overflow, but we will at least be able to compute it. It's going to be some, whoa, I guess it does. Oh, let's check it out. Let's ask what's Fibonacci of 101. Again, we're off by 1 here. Or they're off by 1, right? That's my definition. Oh, no, it looks like we did have overflow here. But you can imagine if I had a multi-precision library that supported arbitrarily large numbers, I could compute whatever, I could compute like Wolfram Alpha does here. I could compute arbitrarily large numbers, and by using memoization, what's the millionth Fibonacci number? Is that a million? That's a million, right? Yeah, what's the millionth Fibonacci number? It's that thing right there. It has 208,000 digits, right? And I could probably do that here too. It's just that I'm not going to get the right answer. But it is going to execute pretty quick, right? Oh, okay, segmentation fault, core dump. That was too big, right? And I'm interested to see why. Let's find out. We've got plenty of time here. GDB A dot out, set args to 200,000. There we go. Run, backtrace. Where did you fail? Oh, I know what failed. What failed? What is all this? It's shortened up here, but if I continue, oops, continue, return, continue, continue, continue. What's going on here? I'm making recursive calls. Even though I'm using memoization to eliminate most of those recursive calls, I'm still going on a deep recursion. How deep is it going to be? 200,000 levels deep, because that's the recursion that you gave it. You want to compute the 200,000th Fibonacci number, you need to do this, right? It's not, oh, there's something different there. Oh, maybe it was just a flicker. All right, yeah. I'm not going to go all the way. All right, there we go, quit. All right, quit anyway, yes. All right, There we go. All right. So memoization allows you to skip unproductive, repeated recursions, right? All right. Let's see. Oh, okay. What you're going to be doing, and let me go ahead and give you some tips on hack. I guess it's 12. Your hack 12. You'll also basically use memoization to compute the binomial coefficients. Right? So the binomial coefficients look like this. You might even recognize them. N. There we go. It looks like that. How do you read that, by the way? Anybody? N choose 2. Right? How many ways are there of choosing k things from a set of size n? Right? So basically, it captures that notion. This is the number of ways to choose k elements from a set of size n. Right? So, for example, how many ways are there of, say that you have, I don't know, how many people are, okay, here, I don't know how many people are on the NCAA football roster? Anybody know? Okay. I know how many people are on an MLB roster. So given 25 baseball players, you need to choose 9 of them to start a game. The number of ways, and forget about pitcher, you can have position players for pitchers and pitchers for position players. You can move them all around. It doesn't really matter. The number of ways to do this is, well, we've got 25 players, or we've got 25 players in the roster, right? And we need to choose 9 of them, okay? Now, normally, you would use a bunch of factorials to compute this. So what it's going to be is 25 factorial. How big is that, by the way? That's huge, right? But you also divide out by repeated the subsets. So what it was, so it gets divided out by 25 minus 9 factorial, and then 9 factorial, okay? So whatever that is, but let's go ahead and employ Wolfram Alpha again here. And you've probably seen it, you might have seen it in this form instead. C25-9, or sometimes C with, if you look on your TI-82 calculators or whatever you use now, there's a big C and an N at the top and a K at the bottom. That's a binomial coefficient that you can use. So there are 2,042,000 ways of doing this. Another interesting way of looking at this is, oh no, I don't know how to play Powerball. How many numbers are there in Powerball? Well, they choose 5, right? But how many are there actually? Nobody knows? Yeah, go ahead. 5 numbers 1, 2, 50. I think, is it 59? 59. You choose 5, and then there's a 6th Powerball, right? And how many are there? Okay, nobody gambles. Good for you. There are ways. There we go. So what's I've multiplied these together. That's your odds of winning Powerball, roughly. Again, I don't know what these numbers are. If there are 45 Powerball numbers and you choose 1, and then there are 59 white balls and you choose 5, this is the number of ways of choosing. So you have a 1 in 225 million chance of winning. Of course, correct for that for however many balls there actually are. That's where these binomial coefficients come in. Okay. So how are you going to compute this? Well, you can compute it using a bunch of factorials, and that's the straightforward way that you would want to do it in practice. But a couple hundred years ago, this guy named Pascal, Blaise Pascal, cool first name, came up with the following identity. Right? That n choose k is equal to, I'm not going to remember it, so I think I can remember it, but I'm not going to be sure. Pascal's identity. There we go. Wow. Okay. Pascal's identity. We'll just search for it. Oh, there it was. I didn't need it. So there we go. You can split it up. You can divide and conquer it into 2 sub computations, where you take n minus 1 and k minus 1 plus n minus 1, choose k. So let me go ahead and go back to this one. It's n minus 1, choose k minus 1, plus n minus 1, or no, it was n choose k minus 1. Does that look right? It's n minus 1, sorry. We don't call that the numerator or the denominator. I don't think that there is a word for those. There. So there's Pascal's identity. You could really easily come up with a recursion to do that. There are a couple of corner cases that I'll let you say. I'll save that for the hack. Basically, when k is 0, how many ways? If I've got 25 players, how many ways are there of choosing nobody? Just one. Don't choose anybody. Right? That's the only way. If I've got 25 players and I want to choose them all, how many ways? So in other words, n choose n. How many ways are there of choosing everybody? Also one. Those are your corner cases. And so you've got your base cases, and then you can use Pascal's identity here. Given an input of n and k, all you need to do is recursively call your function on n minus 1, k minus 1, plus n minus 1, and then k. You don't change the second one. So it's going to look very, very similar to the Fibonacci sequence, except you take two inputs, n and k. And what you're going to find out in hack is the same thing that we did here, that it would take, Fibonacci, there we go, this is the one I want, that it's going to take hundreds of thousands or billions and trillions of years to actually compute this stuff using the naive recursion. What you're going to want to do instead is create a table, an n plus 1 by k plus 1 table, and then fill in your base cases, which are just on the edges, and then pay for the recursion. Pass this big two-dimensional table onto your function, and then look, did I already compute this value? If so, I'm going to use it. Otherwise, I'll go ahead and pay for the recursion, and then once I've paid for the recursion and computed that value, put it into the table. And you will see a huge world of difference, right? And of course, seg fault's there. Let's go with, I think we could do 100,000. It's not going to be that bad. Yeah, we're not going to get the correct answer because of overflow, but you see it only took 0.003 seconds to do that. Just like Wolfram Alpha, probably it took longer to do that just by loading it up from the network. And that's what we were actually paying for there. Here, there's no computation time at all. You're just filling in a very small table. Well, in this case, you're filling out a 1 by 100,000 table, which in terms of computing is small. In hack, you're going to fill out a very small table. I think we only ask you up to like 100 choose 50 or something at most. So 100 by 50 table, that's nothing. Any computer can compute that table almost instantaneously here. Right? Any questions? Of course, the real solution is not even to use memoization. Instead, to use what's called dynamic programming, which is basically here's recursion, right? Here's naive recursion. What we did is we trimmed the tree, we pruned the tree by using memoization. What we can do is we can take out the recursion entirely by instead of, in fact, let's do it here. Instead of making recursive calls, what could I do here? Let's go ahead and get rid of this. Don't even make a recursive call at all. How would you compute the Fibonacci sequence for real if you actually ever needed to do something stupid like this? 4, int I equals, we'll start at 2. I is less than or equal to n, I plus plus. All I need to do is compute the next Fibonacci. Fib table of I is going to be equal to fib table of I minus 1, the one previous to it, plus fib table of I minus 2. All we need is a simple loop. We don't have to have this recursion where we're going so deep, right? Or going so deep into it. And then long x here instead is going to be long x. It's going to be fib table of n. There we go. There. Now there's no recursion at all. I could go up and erase that function if we really wanted to. GCC it. Still run it with, I don't know, 100. And I'm still getting the same results. But now there's no recursion at all. Instead, I'm using basically what's called dynamic programming. You've got your table. Don't bother with the recursion. Just figure out how to fill in the table. Fill it in top to bottom, left to right, or maybe sometimes it's different problems like this one. There's only one row, so you fill it in left to right. Or in some other problems, sometimes you need to get really fancy and then you fill it in diagonally. right, or some other ways. And that's dynamic programming. You don't need recursion at all. Right? You can go back to the original versions of Pascal that don't even support it. Okay? Any questions? All right, on Wednesday, we will begin with searching and sorting. Again, we've got our SAP on Wednesday from 11 to 1 o'clock. I'd encourage you to attend. At least you probably have 50 events where you get free pizza. You're probably pizzaed out by now. But you can come by at least and share your opinion on the program, on the department, and anything else that's on your mind.